Yes, thank you for the introduction. So this work is about trusted execution environments, or more specifically, how do you talk to a trusted execution environment? So first, let me explain the setup a little bit that we're envisioning here. So we have a service that is running remotely in a data center, for example, and we have a client and they want to interact. So the client wants to talk to the service. And if we imagine that the service is processing very sensitive data, you could think of like a confidential compute scenario. We want to protect this execution by means of a trusted execution environment. A trusted execution environment is a hardware extension of many modern processors, like Intel has TDX, AMD has SEV, ARM has an equivalent, RISC-V has an equivalent. And what they essentially do is they protect the code execution from other co-running applications by means of memory isolation, but also from the infrastructure provider by means of memory encryption and by means of shielding application execution from the underlying operating system. But all of this protection really only makes sense if the client can check that it is in place. Otherwise, the data center can play make-believe. So at the start of the conversation, the client would ask this remote trusted execution environment about its state and include a nonce for freshness. And what you get back from the remote side is what's called an attestation report. So this is essentially how remote attestation works. If we look inside of this report, it contains the nonce again to validate that this is a fresh answer. It contains a hash of the software state that has been loaded and a bunch of metadata. And all of this is signed by a key that lives in the hardware at the remote data center side. So it lives inside what we call a root of trust, and it is supposed to never leave this root of trust. So the root of trust would be part of technologies like Intel TDX. If the client now receives this attestation report, they can check the hash of the running software if they like the state of that software. And by looking at the signature, they can verify that the code is actually running within a valid, like Intel processor. Once we're happy with that on the client side, the next step would be to establish a secure communication channel. Secure meaning it should be confidentiality and integrity protected. And we of course want to make sure that it terminates at the machine where we just got the report from. So this is essentially the problem we're addressing with our work. And what we thought is, well, there is already an existing solution for establishing secure communication channels, and that is our trusty TLS protocol. So transport layer security we use all throughout the internet. So our idea is, can we somehow combine trusted execution with remote attestation? And for that, we have a bunch of additional design goals. We want to minimize the modifications to the TLS wire protocol. We want to have no additional round trips of messages during the handshake in order to keep latency low. We don't want any additional payload encryption once the channel is established, so it should be a regular TLS channel once it is established. We want to be independent of the root of trust, so it should not be specific to one technology. We want to be resilient against relay attacks. I will talk more about relay attacks later, but essentially it means the channel must terminate at the end where we just got the report from. And we want additive security. So the remote attestation validity should not rely on the security of the private key of TLS. And also we don't want to make any changes to the certification or attestation infrastructures, the deployment infrastructures, the certification authorities, those are all in place. We don't want to change this too much. So with these goals in mind, let's start looking at how the handshakes look like. So TLS has a handshake. It starts with the client hello, where the client wants to initiate the connection. The server responds with what is called a server hello and then presents its certificate to prove possession of the private key. On the remote attestation side, it looks very similar. We start with an attestation request from the client, and then the service responds with an attestation report. So superficially, they look very similar. So our first idea is, of course, to piggyback these two protocols. And here, TLS 1.3 gives us a very nice feature. So that's the current version of TLS. is that TLS messages can be extended. And this functionality is already part of the TLS standard, is that we can have a cryptographically secure way of amending these messages. So if we look at a standard TLS exchange without attestation, we now simply specify a number of extensions to those messages, like the client hello message would be extended with the attestation request, and the certificate message would be extended with the attestation report. And then we can transport those alongside. Both of these extensions are part of ongoing standardization efforts at the IETF, where the authors of these standardization efforts overlap with the authors of this paper. Taking this idea, if we look at our initial design goals, this already gets us quite far. So using standard TLS message extensions, we make sure that we have absolutely no changes to the TLS wire protocol. It is a standard TLS 1.3 connection that we're using. We also have no additional round trips and no additional encryption, just that the messages get a little bit larger. And the extensions can carry any attestation report, because in the extension, it is essentially a binary blob that we just transport. So now getting to the key of where our protocol is different from related approaches, because this idea has been explored already, is when we talk about relay attacks. And so first I should tell you how a relay attack looks like and then how we can defend against it. So looking at this scenario again, we're now considering that either the provider of the remote service or the operator of the data center wants to trick the client to establish a connection to a machine that is running an invalid software stack, but the client believing that it is valid. So essentially we have a machine in the middle here that runs some evil software and also has possession of the TLS private key to sign the certificate. And we have good software in the back that runs on a valid TEE, runs the valid software. The server's owner now causes the client to connect to the evil version. So the client starts a regular TLS connection with the client hello and sends the nonce for attestation. And what the evil software now does is simply turn around and make its own TLS connection to the good version with a new client hello, because those are cryptographically independent, but passing along the same attestation nonce. So what the evil software now obtains is a valid looking attestation report, which it can simply forward to the client. And since it uses the same nonce, the client thinks the attestation looks good while it is in fact useless. It is not attesting the software state that we're connecting to, it is attesting the software state of a completely different machine. So the result from this is, and this is not a new observation, this has also been established in prior work, that we must link the attestation to the TLS channel. We cannot just slap the protocols together and hope that it works, we must cryptographically link them. And where now our work differs from related work is how we perform the linking. Because a lot of related work performs the linking by trying to make sure that we can attest that the TLS private key lives on the machine that we just got the attestation report from. So we're linking the attestation to the long-lived TLS secret. This works, but if we could ever run into a situation where we can establish a clone of the TLS private key somewhere else, we can again do the same forwarding trick and have a useless attestation at the client side, simply because those attestation reports now will again look the same to the client. So we cannot distinguish if it's from a good or a bad machine. And this is a very hard property for the client to check, that there could never be leakage of the TLS key. Because what would we have to check at the client side? We get a hash of the software state. Originally, we would have to check if this is a good version of the software that we like to interact with. But now we additionally have to check that it is free of side channels. That there is, for example, no vulnerability in it, like Heartbleed, that would allow extraction of the private key by the service owner. Or even the data center provider could mount attacks in the sense that usually the private keys are deployed in the data centers as part of hardware security modules and get loaded into the TEE as they start up. But this loading of the key from the hardware security module is not visible as part of the attestation. So again, we're doing this whole thing to no longer trust the operator, but if we have to trust them that they safekeep our keys, then that's not a useful model. So the current solutions that we have, the attestation essentially relies on where the TLS private key lives and has ever been living. So it relies on the entire provenance of the private key. And that is not a good, from our perspective, not a good solution. We would like to separate those a bit stronger. So here comes our idea how to solve this. We would rather link the attestation not to the long-lived TLS private key, but to the short-lived TLS session secrets that are established once per session. So if we look again at our exchange, what comes to the rescue is another nice feature of TLS 1.3, the current TLS standard, is that it mandates ephemeral Diffie-Hellman key exchange, as it's called. So what that means is that the client hello and server hello messages both contain key material that is part of a key exchange. And the way TLS internally works is that it keeps a running log of all messages which are at the end of the handshake are hashed together, which is called the transcript hash. And this is what is actually signed by the TLS private key in the ordinary TLS protocol to prove possession of that private key. But the secrets that are in the end used to establish the secure communication channel are independent of this long-lived secret. They are derived from those short-lived secrets that are part of the hello messages. So in TLS, this is what gives us perfect forward secrecy. And we just borrow that idea now for the attestation report. We maintain a similar log of all the messages and hash them in the end. For very technical reasons, we could not use the same transcript hash. We could for cryptographic purposes, but not for technical internals of how TLS libraries work. So we had to establish a different kind of hash, which we call the linking hash. Talk to me later why this is the case. And we hand this to the root of trust to establish that the software state is valid. So what this gets us is what we call additive security. So essentially the client and the service exchange messages and keep a running log of these messages and hash them at the very end of the handshake. If everything goes well, those hashes should now be identical. And the service side hands this hash once to the private key for signing to link the session to possession of the private key, and then also completely independently to that, hands it to the attestation root of trust to ascertain that the software is in the correct state. Both of these signatures are passed on to the client, and the client can independently verify them and see, okay, this machine actually possesses the private key, and yes, this machine is running a valid software state. And both these assertions are independent of each other. They're no longer linked cryptographically. The only link is that they are both anchored to the current session secrets. So in summary, this is what we have developed. TLS plus RA combines TLS with remote attestation. It uses standard TLS extensions. There are no changes to the TLS wire protocol. We have no additional round trips and no additional encryption. I skipped the evaluation in this talk because it's not very exciting. You can check the paper. We have an evaluation on throughput, which shows that it is exactly the same as a regular TLS connection. We have an evaluation on latency, which shows that there are some latency increases, but they're just due to the messages getting larger and not due to additional round trips. The extensions themselves can carry any attestation report, so we are independent of the root of trust technology. You can use this with TDX, you can use this with AMD SEV or with TPMs even. And the key idea which distinguishes our work from related work is that we prevent relay attacks by not linking to the long-term TLS secret, but by linking to the secrets, the short-lived secrets in the handshake messages. This gives us two properties. We have independent deployment. We do not have to change the attestation infrastructure or the CA infrastructure of TLS, because both remain independent. And we have independent failure. So remote attestation does not rely on the TLS key and vice versa. If one is broken, we still get the properties from the other. So and that we can say TLS plus RA actually adds the security assertions of both protocols. And with that, I'm finished with my talk, and I'm happy to take your questions.